Now let us revisit the topic of a border effect. When we apply, say for example, a convolution of size 3 by 3 to an input image of size 5 by 5, then the output that comes out will be a 3 by 3, right? But if we do this, then it seems we are shrinking the input to a smaller and a small size every time we do a convolution. So if we have a really deep network with many rounds of convolutions, then eventually the image becomes so small that anything further doesn't make sense. Instead, if we want to maintain the 5 by 5 input, so to obtain a 5 by 5 output, we can pair the input with zeros, which is also known as zero padding in deep learning. So before we apply the 3 by 3 convolution, what I'm going to do is add these extra zeros around my input, so that now when I do the convolution, what I get is actually a 5 by 5 output. So in this way, I will maintain my size of my input image even after doing convolution. Obviously, if I actually have a 5 by 5 filter, then I have to do double padding, that I need additional one layer so that my output size is maintained as the input. And the way we specify this in Keras is when we define conv2d layer here, one filter each of size 3 by 3, I can simply do padding equals same, and this padding equals same means that before applying the convolution, it will zero pad my inputs so that I still get the same output. That is, when I say same, the same shape as the input feature map. Another common idea that's used along with convolutional neural networks is the idea of maxpooling. Maxpooling consists of extracting windows from the input feature maps and outputting the max value of each channel. For example, if we have, say, a 5 by 5 image like this, then what maxpooling does is, say we take a 2 by 2 cell like this grid, calculate the maximum of these 4 values, and keep them as the output in my first cell. Then I look at the next 2 by 2 grid and calculate the maximum of these 4 values, and then save that as the output in my second grid. And I do this for the next grid down here, maximum of these 4 values go into my output. Similarly, the maximum of these 4 values go into my last output. So my first grid, here's my second grid, here's my third grid, and here's my fourth grid. Usually when we are doing max pooling, we want to have the max pool size, in this case 2 by 2, compatible with my input dimension. In this case, this is not compatible because we have 5 by 5 input, but we usually want it to be compatible. Usually Keras throws an error if you can't max pool correctly. So for example, if the input has 26 by 26, then the max pooling helps us achieve feature map of size 13 by 13. Overall, the idea of max pooling is conceptually similar to convolution, but the difference is, instead of transforming local patches via learned linear transformation, that is the convolution kernel, they're transformed by a hard-coded max function. So instead of actually multiplying these 4 values with maybe another 2 by 2 filter element wise, instead of doing that, what we simply do is calculate the maximum of 4 and produce that as output. It's a computationally super light way of doing convolution in one way. So for example, if we have a matrix like this, 4 by 4, and if we apply a 2 by 2 max pool, then what we get is output of this. Maximum of first 4 values appear in the first cell, maximum of these 4 values appear in the cell here, and so on. So why do we need max pooling? So why max pool? The general idea in convolutional neural network is that, say we have a picture, and let's say the picture has a photo of a person, and let's say I want to design a neural network model, let's say a CNN or neural network model, that can check whether the picture has a person or not, right? So then the way we want to design this neural network is such that we have large number of convolutional filters in the first layer, and then a fewer number of convolutional filters in the subsequent layers, and so on, all the way such that at the end we have one neuron that outputs the probability that the picture has a person or not. So everything should gradually, converge to a single neuron such that we only get one output. Because if we get an output that's like, say, 4 by 4, how do we interpret it, right? So say I design a convolutional neural network model that looks like this. I have a first convolutional layer that has 32 filters in it. Second has 64, and third has 64, and so on. My input is a 28 by 28 by 1 input image, a grayscale image. So if we have this, what happens is, here's my input image, and in the second layer, or the first convolutional layer, we have these filters where every input piece of the input volume gets mapped into a single value. And since this is a 3 by 3 filter, it shrinks the input by a little bit, but overall, here's our first layer. And then similarly, we have second layer and third layer and so on. Now, what we want to focus here is something known as a receptive field. So here, the output in the first layer, each pixel in the first layer gets to see a 3 by 3 window in the previous layer. Similarly, each pixel here is an outcome of calculation of not 3 by 3 of the previous layer, but since each pixel here is from previous 3 by 3, effectively this pixel here, it has come up, or the value of this pixel in a way is dependent, or it sees 5 by 5 pixels of the original input image. Similarly, in the third layer, since we are all using 3 by 3, it sees 3 by 3 of the previous input, but here each pixel sees a 3 by 3 of the previous input, and once again each pixel here sees a 3 by 3 of the original input. So effectively, the pixels in the last layer actually see 7 by 7 of the original original image. Now, obviously, the more the final pixels can see, in other words, you have this neuron at the end, the more this neuron can see the big picture, the more likely this neuron is going to give me a correct answer, right? So the 3 by 3 windows in the third layer would contain information coming from 7 by 7 windows in the initial input. So each pixel here depends on a 7 by 7 grid in the input. Ideally, we want the pixels in the subsequent layers to have bigger vision, right? Or larger receptive field. So then we need features from the last convolutional layer to contain information about the totality of the input. This is very important, because the more the subsequent layers have totality of the input, the more likely our final prediction is going to be representative or capturing of the entire input. So how can we achieve that? Obviously, one idea is to increase the filter sizes, right? So increase size of filters. Instead of 3 by 3, I could have maybe 7 by 7 or even 11 by 11, right? But the problem is, when we have larger filter sizes, the number of parameters also become large. So is there any other way we can do this? Obviously, maxpool comes to rescue. So once again, talking about the same neural network model, ideally, what people usually do, or what deep learning models usually have, is we have initial convolutional layers, and then after that, we have dense layers, maybe 128 neurons here, and then finally another dense layer, maybe with 1 neuron, that gives you a value between 0 and 1, like a confidence. right? So a lot of convolutional layers followed by a few dense layers that actually give you the final output. So this is because at the end, we want a probability value, whether that picture contains a person or not, or maybe 10 dense layers, each predicting the probability, whether the number is a 0, 1, 2, etc. So if we add one dense layer to this network, for example, one that has 64 convolutional filters, what's going to happen is at the end of this layer, the output volume is output volume can be this is 64 filters, so the depth is 64 clearly, and here's our 28 by 28 input. In the first round this becomes 26 by 26, and in the second round this becomes 24 by 24. Well, we actually do this 3 times, so this actually becomes further 22 by 22. So we have 22 by 22 by 64. So if we flatten this, the length of the input vector that we're going to get is 30,977, including the bias. This is a lot of parameters that go into a single neuron, right, to predict the output value. So instead of doing this even further, if we add one dense layer after adding 100 neurons, then in the initial layer, I have 100 neurons like these sitting side by side, receiving all of these inputs, and then one neuron taking all of these 100 inputs, then the number of parameters is going to blow up. So having too many parameters will cause intense overfitting issues. So the only way to get rid of this is to, when we have this 28 by 28 input, maybe apply one layer of convolution, get maybe 26 by 26, and then max pool to get 13 by 13, and then convolution to get maybe 11 by 11, and then max pool again to get maybe 11, half of 11, maybe around 5 by 5, and then feed it to a feed forward, the regular dense layers. This way, the number of parameters will be small, and yet also the last layers will see the more of the totality of the input.